Hello, everyone. Today, I want to talk about Tabellion, which is a system for secure legal contracts on mobile devices. This is joint work between the CS department and the law school at UC Irvine, as well as Microsoft Research. So electronic contracts are very popular today, mainly due to the convenience that they provide. They're used in all sorts of contracts, such as real estate sales and leases, venture capital investments, work for hire, etc. Indeed, it is predicted that the market for them is going to grow significantly in the next couple of years, going from about $800 million in 2017 to about $4 billion in 2023. As a result, many electronic contract platforms have already emerged. Here I'm showing you some of the very popular names that you might have already heard of, names such as DocuSign, Adobe Sign, and HelloSign. Most of these platforms already have mobile applications that allow users to view and sign contracts on their mobile devices. But I'm going to go even one step further and predict that the future of electronic contracts is going to be on mobile devices. I see two reasons for this. First, mobile devices are accessible to many users. And second, as I will show you in the rest of the presentation, they can support secure contracts. This is because they have different types of biometrics hardware, such as a fingerprint scanner, an iris scanner, or Face ID. And they also incorporate security hardware features, such as ARM Trust Zone. I do have some evidence for my prediction as well. For example, this Wells Fargo mobile research confirms that momentum is growing for using mobile devices to apply for and close loans. So far, this is all great, but there is one important problem. The problem is that current platforms do not provide strong evidence that a contract has been legally and validly created. To illustrate this point, let me discuss one legal case with you. This case, called In re Mayfield, is a bankruptcy-related case in the state of California in 2016. In this case, the United States trustee brought a motion against an attorney who had used DocuSign to collect signatures on bankruptcy forms. What I'm showing you here is the official court decision. And there are some very interesting insights in the decision that I would like to share with you. Specifically, I want to read one part of the decision for you. It says that this brings the court to another important problem with counsel's arguments. They do not address the ease with which a DocuSign affixation can be manipulated or forged. The USD asks what happens when a debtor denies signing a document and claims his spouse, child, or roommate had access to his computer and could have clicked on the sign here button. So this shows that the platform needs to provide strong evidence on who actually signed a document. So you might now ask, what other evidence does the platform need to provide? The answer to this question is in the law of contracts. So we studied the law and we identified three important requirements for which the platform needs to provide evidence. Before discussing these requirements with you, I would like to first discuss what a legal contract is and how it's formed. A legal contract is an agreement between two or more parties as to something that is to be done in the future. In the rest of the presentation, for simplicity, I'm going to focus on two-party contracts, where we have an offeror and an offeree. The offeror gives an offer. The offeree views the offer and might accept the offer. In this case, we have a legal contract, which is binding. However, it is possible that the offeror might revoke the offer before acceptance by the offeree, or the offeree might just reject the offer or counter it. In all of these cases, the original offer will not be valid anymore. So let's go back to our original question. What requirements do we need to provide evidence for? The first one, and the more obvious one, is what we call signature attribution. That is, the platform needs to be able to demonstrate who actually signed the contract. The second one is mutual assent. It needs to be able to demonstrate that there was an offer, there was an acceptance, and that there was no revocation, rejection, or counter offers in between. And the last one is what we call reading opportunity, meaning the platform needs to demonstrate that the offeree was given a legitimate opportunity to view the contract terms. Note that the wording here is very important. It does not need to show that the offeree actually read the contract, just that they had an opportunity to do so. So with all of this in mind, we built Tabellion. It's an electronic contract solution for mobile devices that can provide strong evidence, as we just discussed. Let me show you how a contract is formed in Tabellion. We have a centralized server that mediates the contract between users. And also we have mobile application that the users can use to interact with our system. To use Tabellion, every user has to first register with our server. To do this, they use their mobile app, they take a photo, and then we show the photo to them on the display, and then they confirm the photo using their biometrics. We use a fingerprint scanner in our prototype. At this point, Tabellion creates a unique digital key pair for this user on this device, and it uses the private key here to sign the photo, and it will then share the digitally signed photo with our server. Another user can similarly can come in, take a photo, confirm, and then send the signed photo to our server. Now let's imagine that these two users want to form a contract. The offeror submits the offer to our server. In contrast to existing solutions, we do not simply take an offer file from an offeror and pass it to the offeree for signing. We render the contract pages that are viewed by the user directly in our own server. We do this because we want to make sure our contract is highly readable when shown full screen on the display of mobile devices. In addition to better readability, this helps us more easily capture evidence of what the user actually saw on the screen. So here I'm showing an example of a contract page that we render in our server. You can see that we pay attention to different formatting issues such as font color, font size, line spacing, margin size, etc., to make sure it's highly readable. We then send these contract pages to the offeror, who views and confirms them one by one, again using their biometrics. When they confirm a page, Tabellion uses the same private key that I mentioned to sign a screenshot that is captured right at the moment of the confirmation. And it will then send all of these signed screenshots to our server. The server now shares the contract with the offeree, who also views them one by one and confirms them, and then submits the signed screenshots to the server. At this point, the server has collected all the evidence, it notarizes the contract and releases it to both users. So the nice thing about Tabellion is that this contract that we release to the users is what we call a self-evident contract, meaning it has all the evidence needed for an independent inspector to verify the correctness and legality of the contract. So I'm showing you the formula for our contract here. There are a lot of details, but there are 4 key components that I would like to further discuss. We call them our key primitives. This is because the correctness of this contract relies on the correct execution of these primitives. 3 of them run on mobile devices and 1 of them on the server. So the first one is what we call secure photo, meaning we want to make sure that when we capture a photo, it's captured by the camera hardware and is not fabricated by software. The second one is secure screenshot, meaning we want to be able to correctly capture the content on the screen when the user confirms seeing something on the screen. The third one is secure timestamp. We need to be able to correctly tag every action with a timestamp that is synced with a global clock, so we can use these timestamps to order the different actions. And the last one is the signature by our notary in our server. We implement the last one using an SGX enclave. I will not discuss it any further. I would like to focus on the client primitives. So we could implement these primitives in a mobile application. Indeed, we have a prototype of Tabellion where it's simply an Android application, and we have the primitives implemented in there. For example, for the secure photo, we use the operating system API to take a photo. And this prototype already provides strong security guarantees to what is available today. However, we wanted to make Tabellion even more secure. And the main concern that we had was that the trusted computing base of our application was large because it contained the operating system. In other words, if the operating system is compromised, it can then tamper with the execution of the primitives. For example, when the app wants to take a photo, the OS can return a fake one. We were especially concerned with this because this means that a user can tamper with the OS on their own device to potentially cheat in a contract. So we thought about how we can further secure our primitives, and our solution was to implement them using a trusted execution environment in a mobile device, or TEE. TEEs are available on commodity devices. They use some security hardware features such as ARM Trust Zone or virtualization hardware to give them an isolated environment from the OS. So now I want to show you how we implement one of these primitives and what the challenges are. For the rest of them, please refer to the paper. So let's see how we can implement our secure photo primitive in the TEE. An easy option for us would have been to take the whole camera stack out of the operating system, including the device driver, and put it in the TEE. This would then allow the TEE to exclusively control the camera and then take photo whenever it wanted. The problem with this is that the camera stack is potentially very large, potentially 100,000 lines of code, and this would have bloated the trusted computing base of our TEE itself. Therefore, we decided to keep the camera stack in the OS, but instead add a little bit of a code to TEE to secure the buffer where the camera stores the photo in. So let me show you how this works. Let's say the operating system wants to take a photo, and it wants the photo to be secure, meaning it wants it to be signed eventually by the TEE. It has to first register a buffer with the TEE. At this point, the TEE will write protect the buffer, and it will wipe out all of its content, and it will only allow the camera hardware to DMA into it. The operating system now continues, programs the camera to take a photo, and the camera will eventually store the photo in that buffer. At this point, the TEE will take a copy of this buffer, put it on a secure frame buffer, and show it on the screen to the user. The user confirms the photo, and then the TEE will sign the photo and release it to the operating system, which can then further give it to the application. All right, so in addition to these primitives, we also, in the paper, discuss how we address different challenges for building a fully functional and highly usable platform on top of these primitives. We discuss how we do contract negotiations, verification, and submission. We also provide a detailed security analysis of Tabellion in the paper. To do this, we came up with the possible attacks on a legal contract platform and analyzed to see how Tabellion protects against them. Here, I want to give you a summary of the attacks and how we deal with them. The first attack is a repudiation attack, meaning after a contract is formed correctly, a malicious offeror or offeree might deny the contract. They might, for example, claim that the signature was not authentic, or that there was no mutual assent, or that the offeree was not given a chance to read the contract. So the strong evidence that we collect in Tabellion, as I discussed some of them earlier, gives us protection against this attack. The second attack is an impersonation attack, meaning a user might want to impersonate someone else and sign a contract on their behalf. Our use of secure photos plus biometrics, and also adding some constraints on what content we expect in the photo to detect user awareness, give us good protection against this attack as well. And the last one is what we call a confusion attack, meaning an offeror might try to fool the offeree into signing a contract different from what they think they're signing. Our use of specifically rendered contract pages and secure screenshots protect against this attack. All right, so we implemented Tabellion. We have two prototypes, one which is an Android application, and we can run it on commodity mobile devices such as Nexus 5X, and another one where we use a TE for our primitives, and we run that on a high-key development board. For both of these prototypes, we use Azure Confidential Computing for our server, which gives us virtual machine with SGX support. So let me show you some performance numbers. Here I'm showing you the performance for a contract offer. This is defined as the time from when an offeror submits a contract until when the contract pages are rendered and ready and downloaded by the offeror and ready to be viewed and signed. On the x-axis, I'm showing you different contract sizes, going anywhere from a couple of pages to potentially tens of pages. And on the y-axis, I'm showing you the execution time. And the color shows you where the time spent here. As you can see, even in the worst case here, the contract does not take more than 20, the contract offer does not take more than 20 seconds. And you can see that most of the time is spent for rendering and for downloading the contract pages. Now, given that users do not sign contracts very frequently, we think that this time is acceptable. Now, let me show you similar results for contract acceptance. Here, this one is defined as from the time that the offeree has signed the contract and is uploading the screenshots until when the server has verified the contract and notified both parties. Again, on the x-axis, I'm showing you different contract sizes, and on the y-axis, I'm showing you the execution time. The color shows you where the time is spent. And again, here you can see this one also does not take more than 35 seconds or so. And most of the time is spent on uploading the signed screenshots. So in addition to performance, we also wanted to evaluate the usability of Tabellion. So we conducted a user study with 30 participants, and we had them sign realistic contracts on Tabellion and DocuSign. We then asked them some questions about the contracts and had them rate the platforms in terms of convenience and readability, and also measured how long it took them to sign the contracts. So here I'm showing you the rating for convenience and readability. On the y-axis, you can see the score based on a Likert scale. And as you can see, users slightly prefer the convenience and readability of Tabellion. So this was great results for us and very promising, because Tabellion is a research prototype, whereas DocuSign is a mature commercial application. So this shows that our usage model, the fact that we render the contract pages specifically for mobile devices and allow the users to view them full screen and flip through them, provide usability benefits. Here I'm showing you how long it took the users to sign the contracts. You can see the time on the y-axis, and on the x-axis you can see different platforms. And again, you can see that the users sign contracts slightly faster on Tabellion. We think this is also because with DocuSign, contracts are not necessarily rendered for mobile devices. So therefore, the users might have to pinch and zoom into the contract, and this might waste their time. So in summary, Tabellion is a platform for secure legal contracts on mobile devices. It can be implemented just as a mobile application, and this already provides great security benefits compared to alternative solutions. But also I showed you that we can leverage the TEE to enhance the security of Tabellion. And finally, Tabellion provides good performance and usability.